Leave a slice of bread exposed to the air, and you are inviting the rapid colonization of a highly successful ecosystem. What we call common spoilage is often the visible architecture of the fungal organism Rhizopus stolonifer. Zooming down to the microscopic level reveals a sprawling, interconnected network of filaments driving this decay. This exposes a biological paradox. From a microbiological perspective, human food is chemically identical to the ideal substrate. It provides dense carbon for energy, nitrogen for structural growth, and the absolutely vital solvent medium required for life processes, water. Left to nature, without deliberate human intervention, almost any piece of food is mathematically destined to become a microbial niche. The organisms that exploit this substrate fall mostly into two categories: spoilage organisms and pathogens. Spoilage microbes, like Pseudomonas, act as chemical dismantlers. They secrete powerful acids and destructive enzymes that physically break down the food matrix, causing massive economic loss and waste. Pathogens present a sharper threat. Bacteria like Clostridium botulinum operate stealthily inside the food, producing lethal neurotoxins without always triggering visible signs of decay. Passive storage offers zero defense against these aggressive biological imperatives. To prevent spoilage, we have to actively engineer the environment to crash microbial metabolism before it can take hold. Microbial life requires specific baseline conditions to survive and replicate. Mapping these variables begins with a nutrient-rich substrate. Next is external temperature, dictating the rate of metabolic activity. Then, pH determines whether a microbe's enzymes function. Finally, the availability of oxygen heavily dictates the expansion of yeasts and molds. We can divide these vulnerabilities into two distinct engineering targets: intrinsic factors inherent to the food itself, and extrinsic factors imposed by the surrounding environment. Among the intrinsic factors, water is the ultimate dependency. It is the mandatory biological solvent for every internal chemical reaction. By manipulating the extrinsic climate, or denying the intrinsic solvent, we snap the chain of microbial survival. Refrigeration is our primary intervention. Its target is extrinsic temperature. We intentionally isolate the food in a closed system and drop the local environment to a strict boundary between 2 and 8 degrees Celsius. Crucially, this temperature range does not eliminate or kill the colonizing microorganisms. Instead, the cold environment alters the microbes' thermodynamics. As the kinetic energy drops, the rotation of their metabolic enzymes slows to a crawl. Refrigeration provides a temporary delay of kinetic energy, retarding the spoilage process rather than permanently stopping it. Freezing is a far more aggressive thermodynamic intervention, one that targets the intrinsic solvent medium directly. This requires pushing the environment to a critical threshold of -18 degrees Celsius or below. At this extreme negative threshold, liquid water is forced into a massive phase change, transforming into a solid ice lattice. This phase change physically locks the solvent. With the water frozen in place, the microbe has no fluid medium to conduct its biochemical reactions. Even though the physical mass of the water remains inside the food, mechanically, the solvent has been completely removed. Freezing halts spoilage almost indefinitely by weaponizing the substrate's own moisture, turning it into an unusable solid architecture. If we cannot maintain energy-intensive cold environments, we can rely on dehydration to deny the solvent medium. This mechanism physically and permanently strips the water vapor entirely out of the food matrix. The goal is to reduce water activity, the highly specific measure of unbound, free water available for microbial survival. Driving this water activity below a precise numerical threshold makes cellular biology mathematically impossible. This produces highly concentrated substrates, like dried fruits and berries, that can sit exposed to room temperature for months. Dehydration is an ancient application of physical preservation that permanently alters the intrinsic capacity of the food to support life. When you look down a modern grocery store aisle, you are looking at the macro results of these physical interventions applied at a global scale. We engineer 3 primary vectors. First, thermal control over the environment. Second, the removal or strict locking of the liquid solvent. And third, the direct elimination of the microbes through extreme physical stress. Whether we alter kinetic energy or induce a phase change, preserving food is rarely a matter of culinary art. It is a strict exercise in applied physics. The ultimate goal is absolute structural stability over time. Modern food safety relies entirely on maintaining these engineered boundary conditions. We control the climate to ensure the global supply remains human nourishment, rather than a rich breeding ground for